Now I did some of this work out ahead of time to make sure that the video wasn't too big. I just wanted to make one video that covered everything that was kind of missing so far in the end of chapter 1 here. So the first thing are examples of some applications, and our applications that we have here are economics, something called equilibrium prices, we'll talk about that in a sec, balancing chemical equations, and then network flows, which primarily would be like an engineering, computer science kind of application. They present it as more how do like traffic patterns work. So if you had some kind of traffic system, one-way streets and things like that, you know how much is coming in and you don't know how much is going out at different intersections, and sort of coming up with a formula for that. Okay, so the application to economics with our equilibrium prices. So basically you have a setup. In this one, we've got an economy that consists of 4 things: agriculture, energy, manufacturing, and transportation. They use A, E, M, and T to represent the bigger words since they didn't want to write them out all the time. And they tell you how much each one sells to the others and how much they retain for themselves. And what your job is to find the price that you would set everybody at so that none of the companies make or lose money. So you want equilibrium pricing. So you want to make sure that everybody makes out evenly in all of these transactions. So the way you do that is you set up how much is going. I set it up this way. So you've got agriculture, 65% stays where it is, 10% goes to energy, and 25% goes to manufacturing. Nothing goes to transportation. And that kind of makes sense. But it all comes from the sentences over here. So it doesn't tell you how much this is, but they tell you the 10% and the 25%. And then you have to deduce what that number is. And same thing for these guys. I just went through and filled out the table, converted that into a system of equations. So how much agriculture pays is equal to all of this. And then move everybody over to the same side. So I just moved these guys over to be with their friends on the other side. And it gets you the system of equations, which you can turn into a matrix, which you then can row reduce. And what that leads to is P sub A, so I was using capital, P sub A is 2.03 times P sub, the last one is T, and P sub E is 0.53 P sub T, and P sub M is 1.17 P sub T. So you could let P sub T be represented by anything that you wanted, and then you can write these guys as multiples of those. It's not anything too fancy. So you would you could set the P sub T price to be 1, then P sub M will be 1.17, 0.53, and 2.03. So everybody else is dependent upon P sub T. So that's what we were talking about in the book. So if you look in the book, often they have information where they talk about free variables. So our P sub T would be our free variable in this one. And then everybody else would be dependent upon that P sub T that we just set up. And then from there, you would just go and finish out everybody. Again, pick whatever you like, dependent on where you want to go. The book has everything rounded to 2 sig figs. I'm not that, I don't deal with sig figs. So you can just go ahead and leave it like this. And if you let P sub T be 100, then P sub M is going to be 1.1 or 117. P sub E is going to be 53, and P sub A is going to be 203. Balancing the chemical equation is similar in setup. So what I did is I just went through and pulled out the different components that we had from the side. So I noticed that we've got a sodium, PO4, a Ba barium, I think, and an NO3. And then I just went through and said, okay, in this one I've got how much of each. And I kept this over here so I could keep track of what my order was. In this one I have how much, and then over here same thing. I can take that and move these guys over to the side, the left-hand side, which makes them negative, and set up a system. Row reduce the system. And what that leaves us with is x1 is 1/3 x4, x2 is 1/2 x4, and x3 is 1/6 x4. So if I let x4 equal 6, then x3 is 1, x2 is 3, and x1 is 2. So I'm just plugging our 6 that we picked down here for x4 into here. And I just pick something, usually if I have nice fractions like this, I pick something that will reduce all the fractions into whole numbers. You could pick 1 here and get fractions out. That's generally fine, but I think in chemistry they don't like that so much. So I just, if I had 6, 2, and 3, I know all of those numbers go into 6 evenly, so I pick 6 here. So my balanced chemical equation, I would have 2 Na3PO4 plus 3 BaNO3 2, and that is BA3PO4 2 plus 6 NaNO3, and that would be the final balanced equation. Nothing too fancy. And you've done that a billion times, I'm sure, in your chemistry class. Next up is our traffic flow problem. So here's the picture that they have in the text. You've got 3 intersections that you're dealing with. 80 cars are coming in, but you don't know how many are going out in each direction. Here 20 cars are coming out from A. You don't know how many are coming in. And B is an enigma over here. You don't know how many are coming in or going out. So for each intersection, you have to come up with an equation that relates your variables and whatever numbers you have. So here I've got x1 and x3 coming in and 20 going out. Down here I've got x2 coming in and x3 and x4 going out. And down here I've got 80 coming in and x1 and x2 going out. So I can rewrite that in terms of normal equations, getting all the numbers on the right and the variables on the left. Turn that into a system, row reduce the system, and it leaves me with this. And what this tells me is that it tells me x4 is definitely 60. That's what the bottom row tells us. The top row says x1 plus x3 equals 20. And the second row tells us x2 minus x3 equals 60. So this fixed, nothing we can do with that. But the other two are dependent on x3. So x1 is 20 minus x3, and x2 is 60 plus x3. So the way you would write this up would be x1 is 20 minus x3, x2 is 60 plus x3, x3 is free. I tried to write that as one word. And x4 is 60. And one thing you can notice about this is if you want these traffic flows to be positive, x3 is at most 20 to make that happen. So those are the general applications that they have in the book. They're not anything I really ever thought about. I've never seen problems like this before for the most part, but they're good applications, something reasonable to think about as far as how you can get something into a matrix form and then work with it a little bit. The next two sections are about linear transformations. This is definitely different than the way the other book I used looked at it. They were much more algebraic and less geometric. So they go through the whole idea of domain, codomain, and range. So normally you think domain and range for functions because these transformations are just functions that are acting upon vectors. So we're going a vector from Rn to Rm, and it's just a rule that assigns something to each x in Rn. Now, Rn is the domain. That's pretty straightforward. Typically, the output is the range, and that's still what's going on here. The set of all outputs, t of x's, is the range. The codomain is the set that you're going to. You might not use all of the things in there, so it's bigger than what your actual range is. So that's why they're throwing this word codomain in there. I did put the image in here. T of x is the image of x under t, because we're going to use the word pre-image a little bit later. A transformation is linear if it holds these two properties. So if you have a sum of vectors inside, then you can break it apart into the transformation. So the sum of the transformation of the sum is the sum of the transformations. That's the fancy way of putting that. And then down here, if you have a constant times a vector, you can pull that constant out and just do the constant times the transformation of the vector. So down here I have a nice little process. I did do that. Dang it. I started the pre-image part over here and I forgot to bump it back over. So, and please forgive my meowing cat. He hates when I come in here and talk to myself. Okay. So the first part is just to find t of 114. And that's just going ahead and taking 114 and plugging it into the formulas that we have. So the top row is the first number minus the second number plus the third number. Then I've got 3 times the first number plus the second number minus the last number. Then the first number plus 2 times the second number minus 3 times the third number. So t of 114 would just be 4, 0, negative 9. Now to find the pre-image, what we're saying when we say that is, what vector do I need to plug in to give 146 as the output? So I just pick A, B, C as random variables to use here. So A minus B plus C has to equal 1. 3A plus B minus C has to be 4. A plus 2B minus 3C has to be 6. We can turn that into a matrix, and I went ahead and put that into the Desmos matrix calculator. It's my new favorite matrix calculator, if you haven't noticed. And it gives us an output. X is 5/4, or A is 5/4, B is negative 4, and C is negative 17/4. So we would get 0, 0, 1, 0, 0, 0, 1. I think this was that. And 5/4. So our vector is going to be 5/4, negative 4, negative 17/4. And that would be our answer for that question. So that's our pre-image. We can do matrix transformations, but that basically boils down to is instead of doing things with letters in them, and again, these letters I carried over from the old book a little bit. The new book does mostly matrix transformations. the way that we get from something that looks like this into a matrix transformation is just by doing a matrix and pulling off the coefficients. Like that. So convert this into a matrix transformation. So T of X would be our AX. That's what a matrix transformation does for us. So if I wanted to find T of 113, I can just take that matrix we just found and multiply it by the vector 113. So I get 1 plus 1 minus 3 is negative 1. Then 2 minus 3 plus 3 is 2. And lastly, 1 plus 2 plus 12, so it's going to be 13? No, 1 plus 2 plus 12, 15. And so it's a quicker kind of way, sorta, of figuring out what your value is. So in this one, we were just looking for the A and for T of 114. Now, they introduced these here because there is a geometric application to this. Suppose you want to transform a point or a shape, which we're going to consider a collection of points, on the xy plane. We're going to start by just, if you want to do just an individual point xy, you're going to take some matrix A, and we'll talk about what you use a little bit in a second. And then you take your point and transform it into a vertical matrix like this. This is another way of thinking about a vector. However you want to think about it, it's just a point x, y. And it's going to give you new coordinates when we do this multiplication, a times this vector. And those new points are your transformed points. Different forms of A will give you different types of transformations. The book has 5 different ones listed out. I've just put them in order here based on what I could fit on the page. So rotations are something I cover in pre-calc even. The standard rotation matrix for clockwise, so going around this way, or counterclockwise, going around the circle the way you normally would go around the circle, is cosine theta, negative sine theta, cosine theta. And you just put your degrees or radians in for theta, and then multiply your points appropriately. Projections take your shape and smush it onto the axis. So you can see here, they had this shape of fish, and the fish got smushed down onto a straight line. Here, they had their fish, and they got smushed onto the x2 or y-axis, depending on how you want to think about it. Projections are important. We actually do some of those in calculus as well, but they just do a quick introduction here. Reflections, there's 6 types of reflections they do. So you could reflect over either axis. You could reflect over the line y equals x, y equals negative x, or over the origin. So it's basically reflecting over both of these. Contractions and expansions are stretching and shrinking along the x and y axis appropriately. So if your k here is small, you would do a shrink. And if k is large, you would do an expansion. Same thing here, shrink if k is small, between 0 and 1, and expand if k is bigger than 1. And shears are the strangest ones of the bunch. A shear, basically, you started with a square with a picture of a sheep in it, because you shear sheep. So they put the sheep in here, and it was a square to start, And what the shear does is it takes the top corner and pulls it over and brings the whole top with it and leaves the bottom, forming this nice parallelogram. And same idea over here. So this is what happens if k is less than 0. This is what happens if k is bigger than 0. And a horizontal shear puts the k and the 1 over here on this side. A vertical shear, same idea. If k is less than 0, you're going to pull the corner down below the axis. Over here, you're going to push the corner up above the axis. So it's just taking your shape and parallelogramming it from nice rectangular or square form. If you wanted to see what happens, so E1, E2 is the way that they refer to these in the book. It's just the point on the graph that you're working with. So if I forgot my little bar over this guy. If I started with my shear from down here, and I picked the corner point, the 1, 1, which would have been the starting point over here before we moved it, and I multiply this matrix times 1, 1, I get 1 plus 0 is 1. K plus, oh crap, that's k plus 1. K plus 1. And we get 1, 1 goes to 1 k plus 1. And then same down here, if I do the transformation matrix times 0, 1, so 0, 1 is this point up here. X is 0, y is 1. I get 0 plus 0 is 0. 0 plus 1 is 1. So 0, 1 is going to be mapping right to itself. And that's exactly what you notice here. This part of the graph, this line right here doesn't move. It's everybody else gets dragged down a bit. So the way they form these in the book, so it says find a matrix A that will give a shear transformation T from R2 to R2 that leaves E1 unchanged and maps E2 to E2 plus 3E1. So if we look up here, in both of these, our E1, our first points, were unchanged. And then E2 was 1, and 3 must have to be our K in this one. So our matrix A is going to be 1, 3, 0, 1. So if I started with, let's see, if we wanted to sort of suss out what happens here, we call this 1 and 1, and we give ourselves a nice little square. I know it doesn't look like a square. And if I calculate out what happens, 1, 3, 0, 1, if I multiply that by 0, 0, of course I'm going to get back 0, 0. Nothing's going to change. If I do 0, 1, from above we should get 0, 1 back. So let's double check. 1 times 0 plus 0 times 1 is 0. 3 times 0 is 0. 1 times 1 is 1. So we get 0, 1 back. So 0, 0 goes to 0, 0. 0, 1 goes to 0, 1. If I do 1, 0, that's going to go to now 1 plus 0 is 1. 3 plus 0 is 3. So 1, 0 goes to 1, 3. And then lastly, I'm going to get 1, and then I'm going to get 3 plus 1 is 4. So if I draw this one out in the orange, what I'm going to get is 0, 0, 0, 1, 1, 3, and 1, 4. So my shear is going to look like this. So that one side down here is in common, but this side, except I can't draw. Be great if I could draw. I went out to 2 instead of 1. So 1, 3 is here and 1, 4 is here. There we go. So this side, again, still the same. This side's been drug up. That's still length 1. These guys, the lengths have definitely changed on. But the sides of these are 1, and these guys are now just a true parallelogram. So that's some of what we're going to do in here. Next week is matrix computations, which will be a little bit lighter for you, I think.